All right. Thank you to the organizers for inviting Annalisa and me to give a talk. On our slide, a third member of our integrable systems group here in College of Charleston is Stefan Lafortune, who's originally a student of he's from the university. He's from Montreal anyway, and um, and we also have a few of our master's degree students who've done projects with Annalisa and Stefan over the years in this same area, and some of them have contributed results, and some of them have contributed imagery that has helped us. Okay, so the talk is going to be mostly about the methods we use to construct closed solutions to the vortex filament equation. And then Annalise is going to more take care of what we can do with them in part two in terms of geometric properties of closed solutions to this equation and also their stability, their linear stability. And I guess we should acknowledge support from the U.S. National Science Foundation through these grants that you can see on the title slide. Okay, so in outline, I will, very briefly remind you of the model of the connection between fluid mechanics and this vortex filament equation. Mostly concentrating, as I said, on the connection with the nonlinear Schrodinger equation, which, as Bob said, we exploit the integrability of that equation in order to say something about closed solutions and get examples of closed solutions to the VFE. Um, there'll be a fair amount of detail about how we do that construction of the closed solutions, and then some of the phenomenology and what we can say about linear stability. That's sort of looking ahead to Annalisa's talk towards the end of this talk. If you all have any questions, please go ahead and chime in anytime. So Annalisa found this cool photograph of a red-winged blackbird blowing smoke rings. I believe this was taken in Alexandria, Virginia, on maybe a cool fall morning. Of course, the smoke rings being formed out of water vapor in the air. And so it's a beautiful kind of picture. And we saw the volcano Etna belching smoke rings the other day. Here's something that's a little bit more down to earth. So the VFE is sometimes known as the smoke ring flow, but we'll call it the vortex filament equation. And remember that, of course, a vortex filament is a thin tubular region of non-zero vorticity surrounded by irrotational fluid. And it moves under self-induction. If you have a small core radius and circulation held constant, then that center line moves with the fluid, and so it points along it. It's just the velocity at those points along the curve. And x I'm going to use as a longitudinal parameter along the curve, and of course t is time. But as you make the core radius approach zero, the dominant term in the expansion after you do some rescaling becomes the binormal vector field times the curvature of the curve. So just to remind you, now I'm going to use x to be arc length. There's s in this picture here. So this really should be gamma sub x, which is, of course, the unit speed. So I've been doing an arc length parameter along the center line of the filament. The acceleration vector is perp to the unit tangent vector, and their cross product is what is the velocity under the vortex filament equation, the time velocity. And that is the unit vector in that direction, that cross product, is the binormal vector of the Frenet frame. Kappa is the curvature, and as I said, x is arc length. So again, this is sometimes known as the KB flow. If you want a simple example, if you had a circle in the plane, its unit tangent and normal are also in that plane. Their cross product is a unit vector pointing perp to that plane. And this equation, since the curvature is constant for a circle, this equation would make that circle translate, sweeping out a cylinder with velocity proportional to the curvature. So the sort of the engine, the thing we exploit in this whole project is called the Hashimoto map, and that's associating a complex function of x and t to this evolving space curve that's a solution of the VFE. So how does that come about? Well, for a space curve, the basic invariants are curvature kappa and torsion tau. And we package curvature and torsion into a single complex valued function of x and t by doing the following. If you think about it in terms of polar coordinates, the sort of the magnitude of that complex function is the curvature, and the argument is an antiderivative of the torsion. Uh, and in fact, to get, oh, and then times a factor of 1/2, which is some people put in, some people don't. And in fact, to get this to satisfy the nonlinear Schrödinger equation on the nose, you have to make sure that the constant of integration in this antiderivative of torsion evolves in a certain way, determined by kappa and tau. But the theorem is, if you do this, and by the way, these will be compatible if gamma satisfies the VFE. If you do this, then you get a complex function that satisfies the focusing cubic nonlinear Schrödinger equation. And this was discovered, as you can see, by Hashimoto back in the 1970s. So as I just mentioned, circles, planar circles evolve by just translation under the VFE. And if the radius, remember, so the curvature of a circle is 1 over its radius. So if I make the radius 1 over a, little a is the constant curvature of the circle, and that's the vertical velocity of these translating circles. And if you make the corresponding Q under the Hashimoto map, it has no x dependence. This is a plane wave solution of NLS. But as you can see, that the theta that's in the exponent there has to have non-trivial t dependence. Well, it's just a constant times t. But we do have to pay attention to this evolution. All right. So translating smoke rings, again, smaller smoke rings would have more curvature, move faster. Okay. Map over into the Hashimoto map to plane wave potentials. So I'd like to give a little bit of an explanation as to what the Hashimoto map is doing. Okay, and this, since I'm a differential geometry, this explanation will be kind of flavored with classical differential geometry. So you may remember the classical Frenet equations. The way you get curvature and torsion for a space curve is that you take the arc length derivative of the unit tangent, that's kappa times the unit normal, and then the arc length derivative of the unit normal vector is minus kappa t plus tau b, and finally b sub x is minus tau n, where t and n and b, of course, have the Frenet frame, the orthonormal frame along the curve, and kappa and tau can be used to determine that curve up to a rigid motion. So an alternative to so one of the by the way, one of the problems with the Frenet frame is that it's ill-defined at inflection points. Okay, places where kappa is 0. So you might have this thing where n is momentarily undefined at an inflection point, and so that's not so nice. There are alternatives to the Frenet frame which are not so well known, and one of them is called the natural frame. What at least we call it that. It's not. There are other people have other names for it, where you still retain that unit tangent vector, of course, but then you have a different choice of vectors of unit vectors in the normal plane, such that they have the x derivative of each one is a multiple of the tangent plus a constant multiple of the other normal vector. So it's sort of like they spin at a constant rate in the normal plane of the curve while also bending the direction of the unit tangent vector. And these will usually be well defined when you go across inflection points. And the relationship to the Frenet frame is, well, I mean, this is easiest to write if you use a little bit of complex notation. If you write those two new normal vectors as u1 plus I, u2, so a single complex value normal vector, then it's a certain e to the I theta times n plus ib, where theta is the appropriate antiderivative of torsion. Well, antiderivative torsion minus a constant, I should say, to account the fact that there's this constant spin added in the normal plane. But
So
if you, yes, go ahead.
so implicit in what you're saying is that it may sometimes be useful to take C non-zero.
Yes, and I'll explain that in a moment.
Yeah,
But
okay.
if you do say it, if you do make it zero, which is the simplest choice, then you get what Richard Bishop called frames of least rotation. He wrote an article on the MAA Monthly, American Mathematical Monthly, about there's more than one way to frame a curve, and in that case, this is just antiderivative torsion, and we see from this formula that Q is exactly well up to a factor of 1/2 the two natural curvatures for that spin zero natural frame. So it's just a different way of packaging the Frenet type invariance now as a complex function of x and t. Now, we would like a way of inverting the Hashimoto map. In other words, going from a complex valued function of x and t and a solution of the nonlinear Schrödinger equation back to a space curve. And the way that's done is through the mechanism of the AKNS system, Aulowitz, Kaup, Newell, and Sager, also known as the Zakharov-Shabbat system, your Russian school. So this is equivalent to the Lax pair. The nonlinear Schrödinger equation is an integrable PDE, and so it's got all the wonderful things about integrability, including inverse scattering, and that's mediated through the Lax pair. So this is a system for a two-component vector-valued function of xt and also the spectral parameter lambda. And this is compatible. This should be phi sub x here. This is compatible if and only if Q satisfies NLS. And now, when Q is in the image of the Hashimoto map, in other words, if it comes from a space curve, we can recover that curve and its natural frame from solutions to this AKNS system. So here's how you do it. So we're going to identify R3 with the Lie algebra SU2 by just picking a basis for the Lie algebra and declaring them to be the unit vectors, orthonormal unit vectors, which they are for, I think, for minus 1/2 times the Killing form. So I've identified R3 with the Lie algebra SU2. And what's interesting, what you might notice about the spatial part of the Lax pair of the AKNS system, rather, is that when lambda is real, this coefficient matrix is in the algebra SU2. And so that means that if I take the lambda derivative if I take a fundamental matrix solution of AKNS, and that'll be, as I said, SU2 valued when lambda is real, because this is algebra SU2 valued coefficient matrix. And then if you take phi inverse, now phi is a matrix rather than a vector, phi inverse d phi d lambda, that gives you a matrix in the algebra SU2 evaluated when lambda is real. That is, we can identify that with a vector in R3, and that vector satisfies, that's our solution of the VFE that generated, when lambda is 0, I should say, when I set lambda equals 0, that's the solution that generated Q. And you also get for free the solutions of the natural frame equations along this curve. With a certain spin that's just twice the value of lambda at which you evaluated. Now, I should say this is not quite a solution of VFE because it's got a constant slide along the tangent direction. But if you kind of, changed coordinates a little bit to get rid of that, you could do that. So this brings, I want to answer Bob's question about why bother with the natural frame equations when C is non-zero. And if it's okay with you, I'm just gonna stop sharing for just a moment. Can I do that and still see the board? Would that work, Sarah? I'm just gonna write something on the board behind me.
That sounds good to me. I think it's fine.
All right.
Yeah, you should be able to stop sharing and
okay,
and then
so
return to sharing again.
Yeah. Okay. So if you so diagrammatically, where are my notes? Okay, there they are. Excuse me. So diagrammatically speaking, we had we have this VFE equation, and we apply Hashimoto, and we get a solution to NLS. Okay, and the thing about this talk is, as I said, about closed solutions. If you have a closed curve that is periodic in X, then it turns out that Q, as formed under the Hashimoto map, is not necessarily periodic. Okay, because what did Hashimoto say? It's Q is kappa e to the I antiderivative of torsion ds. Well, kappa and tau will be periodic, but integral of tau will not be periodic unless it's got, average value 0. So this Q you get here will only be quasi-periodic. Will be periodic about, if gamma of X plus L, let's say, is gamma of X. So this is a closed curve of length L, then Q will be quasi-periodic. Q of X plus L will equal to e to the I, integral of torsion ds times Q of X. So it won't be periodic, but it will be related to a periodic solution of NLS through a Galilean transform, which consists of doing a sort of a Galilean transform in X and T and multiplying by the appropriate unit modulus function of T. So let me just not write the details in, but there's a dead-on periodic solution of NLS that's related to this. And moreover, you can get back to your original curve if you do sim at a related non-zero lambda. So that's closing the loop between periodic curves and periodic NLS solutions. That's why you want to use sim at a non-zero lambda value. All right. Does that answer your question more or less? We can talk about more afterwards, but if you want. But
Oh, perfect.
Okay, great. All right, let me go back to screen sharing. There we go. So again, this is about the sim formula that, or sim-Pohlmeier formula, I should say, that lets you construct curves that evolve by VFE up to a tangential slide from a fundamental solution matrix for the AKNS system. There we go. Okay, so now into the details of how we actually get our closed vortex filaments. And as I hope my explanation on the board showed you, I want to start by getting together some periodic NLS solutions, periodic in X. Okay, so those are constructed by considering the Floquet spectrum of such a solution. Okay, what does that mean? Well, we can take the spatial part of the AKNS system, and remember there was that lambda in there, and I can rewrite that system as an eigenvalue problem. I can rewrite that AKNS system, the spatial part, as an eigenvalue problem. For a certain first order linear differential operator, it's a matrix differential operator with a zeroth order part that just depends on Q. And so that spatial part of the AKNS system is equivalent to this equation. And we can ask for certain, okay, if you have an eigenvalue lambda, for a particular lambda value, look at the solution of this system. If Q is periodic, we could potentially have periodic solutions for this system. Now the Floquet spectrum of that operator is a set of lambdas such that this system has a solution which is bounded in X. In other words, it's got, if you look at how much it grows over, let's say, one period in the X direction, that growth rate has to be, well, since it's complex, it has to be a unit modulus, multiplying by a unit modulus thing, or by a unimodular matrix. And this is not quite the definition of the Floquet spectrum because it's actually equivalent to it. But if you think about when this system has let's say a solution that grows by, again, that grows in a bounded fashion in the x direction, one example would be something that just gets multiplied by a complex scalar of unit modulus. So that would be an eigenfunction of the transfer matrix. Okay, this transfer matrix is we have a fundamental solution matrix of that linear system, and we evaluate it after one whole period, having started at the identity. That's the transfer matrix, and the eigenvalues of that are correspond to solutions that grow by just a scalar multiple over one period. And those, because this transfer matrix has determinant 1, then the eigenvalues are reciprocals of each other, and they're determined by taking its trace and just solving this equation. So those are called the Floquet multipliers. They're telling you, for every Floquet multiplier, there'll be a solution that grows by that multiple over one period in x. And if this trace is between -2 and +2, then the Floquet multiplier is unit modulus. So we have something that's bounded over one period and hence bounded for all x. By the way, this Floquet discriminant, of course, is an complex analytic function of lambda, and that means mu is sort of a branched function of lambda. So you can think of mu the multiplier as living on a Riemann surface that double covers the complex lambda plane. So where does this, what lambda values belong to the Floquet spectrum? Well, for one thing, as I mentioned earlier, when lambda is a real number, the transfer matrix, which starts at the identity, will belong to Lie algebra SU2, which is compact. Or sorry, the Lie group SU2, which is compact. And so, if the transfer matrix is just multiplying by an element of a compact Lie group, the eigenfunction stays bounded for all x. And so every real lambda belongs to that Floquet spectrum. And moreover, this whole spectrum is conserved by the time evolution under NLS. And so in some sense, the fact that NLS is an integrable evolution with all these conservation laws is all wrapped up in the preservation of the Floquet spectrum. At least in the case where Q is periodic, because all that information in the Floquet spectrum more or less corresponds or can be used to generate all the conservation laws. So what does a Floquet spectrum look like? Well, as I said, it contains the whole real axis, but it will also contain branches that come off the real axis and maybe even disconnected ones I haven't drawn here. And those branches will terminate in what are called simple periodic points. Moreover, the Floquet spectrum is symmetric under complex conjugation because of a certain symmetry in the transfer matrix. These places where these branches terminate are called simple points, and they're simple zeros of delta squared minus 4. Okay, that's where mu is equal to 1 or -1. You have that simple single zero for delta squared minus 1. And so at those points, you'd have a single up to multiple periodic solution of the AKNS system, periodic in X. And the simple points are part of a more larger set of periodic points where delta is plus or minus 2 and the Floquet multipliers are plus or minus 1, where you'd have where the spectral the AKNS system has solutions which are periodic or anti-periodic. And critical points of this Floquet discriminant are called, well, critical points. And those which are where you not only have a critical point, but delta is plus or minus 2 or higher order multiple points. Since this is, the spectrum is remember, this is defined by I don't know if I can write on this or not. Probably not. Okay, so remember this spectrum is defined by saying delta is real and between plus and minus 2. So so at places where d delta d lambda is 0, that's one of those are these corners where branches come off of other branches of spectrums of the flow case spectrum. So I've kind of indicated by sort of a gray dot these critical points, and they are, well, critical for making closed solutions to the vortex filament equation. So let's look at some examples. So corresponding to, as we saw earlier, just a plain old circle. Okay, so let's say radius is, let's say the kappa is 2, so the q is identically equal to 1. And so that would correspond to radius 1/2 and length pi. Well, here's the flow case spectrum of that. And q is constant in x, so I don't know what you mean by the period of q, but let's just say L is pi to go with the circumference of the corresponding curve. And we just have that flow case spectrum just has 2 simple points, 1 critical point, which is also a periodic point. So these x's are double points where you have a second order 0 of delta squared minus 4. Now, if we just lengthen the period, we take double the period corresponding, let's say, going around the circle twice and saying that's our period L, then you'll pick up more double points. You'll get more double points in the flow case spectrum, and those are kind of illustrated by these additional x's that have appeared along the imaginary axis and also between each of the x's we had before. And as sort of a deformation of that double covered circle, you can actually pop it out of the plane in a way that Annalisa will talk about more explicitly tomorrow to get a trefoil knot. And as you do that, the flow case spectrum deforms. Actually, this double point is opened up into 2 simple points, and this piece of the imaginary axis is bent into a curved spine. Okay, any questions about this this example of flow case spectrums and their corresponding? I guess this is supposed to be kind of tantalizing for setting up for Annalisa's talk later. Okay, so the periodic solutions of NLS and their flow case spectrum are sort of two ingredients that we want to use to make closed solutions to the vortex filament equation. So let's look at how we would get, first of all, periodic NLS potentials. And that's through, well, it's kind of like I have to move in some heavy machinery here. That's done for us through the algebrogeometric construction of solution to NLS. So I need to talk about how that goes. So you saw earlier that when we have a periodic solution Q to the nonlinear Schrödinger equation, we've got this associated Riemann surface where the flow K multipliers live. So let's construct such a Riemann surface. Okay, it's a double cover of the complex plane, so it's a hyperelliptic Riemann surface. It's going to have a bunch of branch points that will come in complex conjugate pairs. And as we maybe saw, every branch point is, every spine terminating at a couple of branch points is also going to have one corner in the middle where it branched off another thing. So there's going to be G+1 of those critical points. Okay, so let's say you wrote down such a hyperelliptic Riemann surface, and it's easy to write those down. You just say, just the product of lambda minus lambda I, including the conjugates in this product, and just say, nu squared is equal to this thing, and that's the equation of a hyperelliptic Riemann surface, and its genus is G. Now, we can, there's some natural functions that come associated with such Riemann surfaces. One of them is the Riemann theta function, which is expressed as an infinite sum here over an integer lattice in G-dimensional integer space. And this is a rapidly converging series, so it's very good for numerics. And the coefficient here, this script b, is based on that's made up of the periods of certain holomorphic differentials on the Riemann surface. A genus G Riemann surface will have G independent holomorphic differentials, which can be built out of the coordinates in this equation, the lambda and nu coordinates. But what we usually do is we pick a normalized homology basis on the Riemann surface. And the normalization, by the way, is that it's got A cycles and B cycles, G of each of them. And the A's, the dot with each other to be 0. The B's dot with each other to be 0. And A dot B is, I think it's delta ij. And then corresponding to those A periods, you normalize the holomorphic differentials so they have, have a delta ij inner product with integrals along the A periods times, for convenience sake of convenience, 2 pi I. And then you take the B periods of those holomorphic differentials, and that gives you a negative a matrix of negative definite real part here, and that's what makes this rapidly converging as a series. Okay, so you've got a Riemann surface, hyperelliptic Riemann surface of genus G. You've picked some basis of homology basis, and you make your holomorphic differentials from that. And then what we need, though, is a function that really will solve the AK and S system. And that was sort of cooked up by Krzywer and Eates and Previato in the 1970s and 80s. And we can pick a unique function by making the following specification. We want a function of lambda, well, actually really living on this Riemann surface, and of parameters x and t that's meromorphic on most of the Riemann surface, except for, by the way, this Riemann surface has 2 points at infinity over complex lambda equals infinity, because lambda equals infinity is not a branch point, so there's 2 points. And I guess I better stop that. We pick a divisor on the Riemann surface and ask that the poles of this meromorphic function be inside that divisor. We prescribe its essential singularities of those 2 points at infinity, infinity minus infinity plus, in a way that depends on x and t. And with all that input, it turns out we can actually write down in a unique way such a function. And it's kind of a nightmare formula. Its ingredients are that theta function I showed you on the previous slide, evaluated at a linear combination of x and t, with terms that depend on the Abel map. So it's as I said, it's a function of x and t and a point on the Riemann surface. And remember, the Abel map is, can I get out of the comment mode here? Okay, that Abel map is what you get when you pick a base point and integrate along a path of holomorphic differentials. So that gives you a vector in G-dimensional complex space. And all this information anyway can be determined by doing certain integrals on your Riemann surface. So you bring that package all together, and this vector valued function turns out to satisfy the AK&S system for the NS solution that's given by this quotient of theta functions with an exponential factor up front. So this all kind of comes, off the shelf, and we've got Mathematica code that can just, you can just pick some branch points and it'll do all the integrals. And although I have to say with Mathematica, you have to be really careful. It'll make branch cuts on you that you don't want. And then you can just, you've got your NLS solution. Now, we wanted to have something that is periodic at X. So what do you have to do to maintain that? Well, the theta function is 2 pi periodic in any of its input directions. It's a function of C to the G. So you have to make sure that these the coefficients of vector V are rational, rational related numbers. And this coefficient of X here that cause Q to be periodic, quasi-periodic, you can actually take care of this by shifting the branch points to the left or right in the complex plane. You actually can get rid of that. So really, periodicity of Q is just controlled by the components of this vector V, which are related to the B periods of certain abelian differentials on the Riemann surface. Once you have that periodic Q, however you achieve that by choosing your branch points carefully, then you can try to get a closed VFE solution, periodic in X. And how do you do that? Use the SIM formula. Remember, what you need with that is a fundamental solution matrix for the linear system, for the AKNS system. And what you do is, well, for every lambda, there's 2 points on the Riemann surface. So you just evaluate the Baker function at those 2 points above and below, and they give you the column of the fundamental solution matrix. I mean, you'll have to normalize it so it starts at the identity, but still, that's how you do it. When you do that identification of SU2 with R3, the sort of the E1 component of the curve you get looks like this, right? So this is the ingredients of this. You've got log of the theta function. The gradient is, the multi-directional gradient in G-dimensional space, dotted with the derivative of the Abel function, of the Abel map rather, with respect to lambda. But the point is, if you want something that's periodic in three-dimensional space now, this is no problem if the theta is already periodic in X. So this will be periodic in X, but you really have to watch out for this linear growth here. This will not be periodic. So you have to make sure that this omega 1 prime, which is a certain differential called the quasi-momentum differential, which again is uniquely determined by your Riemann surface. You have to make sure that that is evaluated at a point where this numerator is 0. That's just a polynomial. There'll be G plus 1 of those points where you can make sure that this quasi-momentum is 0. So that's a necessary condition to get a gamma that is smoothly closed in three-dimensional space. Okay, can you hear me?
Yes, we can now.
Okay. Sorry, people. Let's see. Check, check, check. Can you hear me?
Yes, we can definitely hear you.
Okay. Thanks. Great. Okay, so equipment failure in midstream there. Okay, so I was on my way to talking about what do you have to do to construct closed solutions from a periodic NLS potential. And what you have to do is make sure that you've chosen a point in the Floquet spectrum where the quasi-momentum is critical. So omega 1 primed is 0. And also the Floquet discriminant is equal to plus or minus 2. In other words, a periodic point of the Floquet spectrum, this is also a 0, the quasi-momentum differential. And by the way, this Floquet discriminant and quasi-momentum function omega 1 are related by this equation. So when delta is plus or minus 2, that's the same as saying that that L times omega 1 is like a multiple of pi. Yeah. And as I said, the zeros because of this relation, the zeros of omega 1 primed will occur at corners of the Floquet spectrum. So bottom line is, if you have a periodic NLS potential Q that's come from this algebraic construction, you have to then make sure that you plug into the SIM formula a lambda value along the real axis that is A, a periodic point, and B, also a corner of the spectrum. So maybe at this moment, I'll just go back to this picture. Just a second. So here we have a bunch of corner points, okay, that are critical points of the causal momentum, but they're not periodic points. The periodic points are the ones with these X's. They're not double points. But if we go to the next slide down here, and I don't know why I can't get out of this, okay. These ones are both corner points and periodic points, and no wonder that we can plug into the SIM formula and they correspond to a closed curve. Okay, how about more examples of satisfying these closure conditions? Well, again, with multiply covered circles, again, taking the length to be 2 pi for example, the plane wave solution has Floquet discriminant that has this formula. And the only zero for that for the quasi momentum is at the origin in the lambda plane. And that's a double point only when A is chosen to be an integer. So what we get then is a bunch of, when A is an integer M, we get a bunch of multiply covered M times circles, which of course, translate when you move. And each of them, there's exactly one reconstruction point where we can get a closed curve. But these multiple covered circles will be important for what Annalisa talks about later, because they're kind of our starting point. Remember my picture with the bending the spectrum that I just kind of re-showed you, showed how I kind of desingularized a double covered circle to get a trefoil knot. Okay, that can be done in a more systematic way, in a way that Annalisa will describe. Now, a really interesting family of examples are the genus 1 potentials, where the Riemann surface you use to make the Baker-Akiser construction of an NLS solution is genus 1. So in that case, since 2G plus 2 is the number of simple points or branch points, so we have 4 branch points, lambda 1 bar, lambda 2 bar, and 2 critical points where their spines intersect the real axis. And since the theta function only has one scalar input now, plus it's that exponential out front, the corresponding Q's just depend on 2 linear phases, one in this exponent and one inside the theta function, which for an appropriate choice of branch points can be just a plain elliptic CN function or conoidal potential. And by the way, the elliptic modulus one uses for that is just determined by differences between this ratio of differences between the branch points. And as I said before, you can actually slide the branch points to the right or left to actually eliminate this E coefficient. So this is automatically, so you can easily arrange that this is periodic. And moreover, if you're careful, you can arrange the branch points so that the double points along the real axis line up with one of the corner points, and so that we actually get a point where you can plug into the SIM formula and get a closed curve, like the I guess this is a 2-5 torus knot that we see here. Now, these genus 1 filaments that you get out of the SIM formula are known as Kita filaments. So Kita studied back in the 80s solutions of the vortex filament equation that move by a rigid motion. That is that, up to a slide along the curve, there's a screw motion. That's the general, that'll be a general rigid motion in Euclidean space. They move under gamma sub t is kb. That equals a killing field, the restriction of a killing field along the curve, plus possibly a tangential component. And they showed that all such filaments are center lines for Kirchhoff elastic rods. So we saw elastica in one of the talks yesterday. Elastica, of course, are critical points for a Lagrangian where you don't have this torsion term, classical elastica. But if you add in that torsion term, then you get these elastic rod center lines. David Singer and I showed that for appropriate choices of these constants, these Lagrange multipliers, you can realize all torus knot types through these elastic rod center lines. So here's just a few of them drawn with Mathematica. And I should mention that my notation maybe needs a little bit of explanation here. When I write a pair of integers, the first one's always going to be positive, and then the second one could be negative or positive. When I'm using that to describe a torus knot type, the first integer is how many times it goes around the torus the long way. So this is a 2, 3, or goes around twice. And the second one is how many times you go around the waist of the torus, but with a sign depending on whether it's left-handed or right-handed. So this actually has negative torsion, so it's a -3, a left-handed 2, 3 torus knot, and similarly for this one here. Whereas this one goes around in a right-handed way as you go around the torus in a counterclockwise fashion along the long way, and that's why that's called a 2, 7. And of course, these are mirror images of each other. And David and I showed that you can kind of tweak the parameters and boundary conditions to achieve any torus knot type. But more is true than that. Now, all these shapes, as you may be able to see from these pictures, especially the overhead view of this one, that they're composed of congruent pieces. And that's because they come from NLS solutions that are basically made that are periodic in X. And so that means the curvature and torsion are periodic in X. And so this is made up of a bunch of congruent pieces fitted together. So then particularly they all have rotational symmetry, this has threefold rotational symmetry, but so it's given by the absolute value of the second integer in this. This is an instance of what's called the elastic rod homotopy, and I will just kind of say this really quickly since I'm running out of time. For a fixed rotational symmetry group, such as in this case, 120-degree rotational symmetry, there's actually a one-parameter family of elastic rod center lines that pass from an unknotted circle to a 2, -3, in this case, trefoil knot, and that's accompanied by a deformation of the Floquet spectrum for the corresponding Q. So what we want to do in the second part of this talk is sort of drill down into this deformation procedure and actually use it to build filaments of increasingly complex knot types. And I think I will leave it right there since it's 10 to 3.